Hello everyone, I am Pallavi Jain from IIT Jodhpur, India. I'll be speaking about partition aggregation with the project interactions. This is a joint work with Nimrod and Lauren. Participatory budgeting is a democratic process in which community members decide how to spend public money. So suppose we have this set of four projects: building school, two parks and a bus stop, and every project will incur some cost, and we also have some fixed budget, let's say B. Now we want to choose a set of projects within our budget B. So one option is that it could be just decided by the organizer, or we ask community members for their opinion, which is what done in participatory budgeting. We ask community members to either approve or rank or give numerical utilities over the projects. And now the goal is to choose some projects that maximizes the voter satisfaction and the total cost is within our budget. So participatory budgeting has gained a lot of attention in the last few years due to its practical applications. But the challenge in the classical model is that it usually ignores the project interactions. By which I mean that suppose the project of building a school and bus stop are geographically close to each other, and maybe this school is in some remote location. Now if we build a school but there is no bus stop nearby, then it is difficult for kids to go to the school. Similarly, if we build a bus stop in such a remote location and there is no school or something else, then it is of no use. So we can think of these two projects as in complement to each other. Similarly, if we suppose have these two parks geographically close to each other, then many community members won't like to have two parks in the same area. We can think of these two projects as in substitution to each other. And there could be even other kinds of interactions between the projects. So, but in this project, we considered substitution as fixed and complementarity fixed. So in IJCAI 2020, we considered participatory budgeting problem with project interactions. But the question that remained open there was, how do we get interaction structures? So there we assume that it is decided by the organizers, which is of course one option. Another option is that we ask voters to give interaction structures, and then organizers aggregate those structures using some rule and use it as a global structure. So for example, this is one possible interaction structure where these two parts are in substitution to each other. So we considered this problem and call it as partition aggregation problem. So formally, we are given a set of projects, a set of voters, where every voter corresponds to a partition of projects. And we want to find an aggregated partition S. Now the question is, how do we find good aggregated partition? So here we try to adapt the idea of multi-winner election rules, where we want to maximize the satisfaction of the voters. So here suppose every voter gets utility U using some utility function F. Now given this utility function, we use a utilitarian approach where we want to maximize the sum of these utilities. Another approach that we use is the egalitarian approach, where we want to maximize the minimum of these utilities. So if we have the utility function F, then we have some aggregated functions. So now our next goal is to define this utility function F. So I'll first define utility function for substitution structures. So the first utility function is number of pairwise agreements. So suppose this is a partition of a voter V and this is an aggregated partition. Next we will compare every pair of projects. So suppose if we look at this pair of projects, school and green park, then these two projects are in same part in PV while these are in different parts in S. So voter V gets utility 0 from this pair of projects. So similarly, we compare school and the another park, then these two projects are in different parts in both the partitions. So we give the value 1. This is how we compute the values for every pair of projects. And now the utility that a voter B gets from the partition S is the sum of these values, which is 3 in this case. Another function is number of pairwise agreements minus number of merging. So here we try to capture the idea that if two projects are in substitution for me, but these are not in substitution in the aggregated partition, then I'm okay. Because essentially I'm okay with funding one project from this part, but if you want to fund more than one project, then I'm okay with it. But if two projects are not in substitution for me, but if they are in substitution for, in the aggregated partition, then I'm quite unhappy. So this is what we try to capture in this utility function. Suppose again this is a partition of a voter and this is an aggregated partition. Again we compare every pair of project. So if we look at these two projects, then these are in same part in PB, but in different parts in S. Then as I said, I'm not unhappy, so I give the utility as 0. Next, if we compare these two parts, then these are not in substitution for me, but these are in substitution in the aggregated partition, so I give the value -1. And if two projects are in same or in different parts in both the partitions, then we give the value 1 as earlier. So this is how we compute the values for every pair of projects. And now the utility that a voter V gets from S is the sum of these values. So next we define partition aggregation methods. So as we discussed earlier, we have utilitarian approach and egalitarian approach. So if the utility function is PA, then we call the problem as total PA. Similarly, we define other aggregation methods. Next, we'll quickly discuss the computational complexity of these problems. So total PA, we can see that it is same as cluster aggregation problem, which is already known to be NP hard. Using the same results, we have NP hardness even for 3 voters and NP hardness even when every voter has at most 2 parts. So complexity questions are resolved due to the similarity of the problem with the cluster aggregation problem. Next, we study total PAM. So here we prove that the problem is NP hard even when every voter has at most 2 parts. But here we don't know what happens for the constant number of voters. So that question remained open, and the parameterized complexity with respect to the number of voters remained open for total PAM. And we can see that for total PA, the problem is W hard with respect to the number of voters. For egalitarian PA and egalitarian PM, we prove that both the problems are hard even for 3 voters. So again, we cannot hope for FPT algorithm with respect to the number of voters. Next, we define some axiomatic properties. The first property is the unanimity. That is, if all voters are unanimous with respect to a pair of projects, then the aggregated partition should also agree with the voters regarding this pair of projects. So if we consider these 3 partitions, then if we look at a project of building school and bus stop, then these two are in different parts in all the 3 partitions. Then in the aggregated partition also, they should be in the different parts. So we prove that total PA and total PM satisfy this property. Egalitarian P does not satisfy this property, and for egalitarian PM, the question is over. The next property that we define is the majority-based aggregation, which is the relaxation of the unanimity. So here we want that aggregated partition respect the opinion of the majority of the voters. So if we look at the project of 2 parks, then for PV1 these are in different parts, but for PV2 these are in the same part. So even in the aggregated partition, they should be in the same part. So we prove that total PA satisfy this property, while other aggregation methods do not satisfy this property. Our next property is independent of irrelevant projects. So if the restriction of some 2 profiles to a pair of projects is the same, then the restriction to this pair of projects of both aggregated partitions should also be the same. So if we consider the profile P and P prime, And then if we restrict ourselves to these two projects, Green Park and bus stop, then we can see that for two voters, these are in different parts in both the profiles, and for one voter, these are in the same part. Then in if we restrict the aggregated partition of both the profiles on Green Park and bus stop, then that should be the same. So we proved that total PA satisfies this property, while egalitarian PA does not satisfy this property, and the question remains open for total PA and egalitarian PA. Next, we define a utility function for complementarity structures. So here we capture the idea that projects in a part are useless unless we fund all the projects in a part. So formally, so suppose this is a partition of a voter B and an aggregated partition S. Then we can see that there is only one part which is common in both the partitions. So the utility that a voter B gets from S is 1. So again here we use the utilitarian approach and egalitarian approach, and both these problems are NP hard. And then we studied the axiomatic properties, unanimity and majority based aggregation for the complementarity structure. And total comp and egalitarian comp both satisfy the unanimity property, while they do not satisfy majority based aggregation. Some of the future directions. So some of the open questions we already saw. And some questions are, it would be nice to identify some tractable cases. It is possible that some restrictions to the partitions make the problem tractable. Another direction is to look for the aggregation methods when partition has both substitution and complementarity effects together. So currently we defined aggregation methods when either the partition has substitution effect or complementarity effect. But things do change when we have both the effects together. Another direction is to study the parameterized complexity of the problem and design approximation algorithms for the problem. Thank you.